see my my screen very clearly, right? So first of all, I want you guys to know that, and given this is a through thickness crack in an infinitely unwound plate and subjected to the tensile stress. For example, for this one, so this is a through thickness the crack, the 2A, and thickness is B, and this is a remotely applied load sigma. For this one, and so this is we know that Graves from our previous lecture, Graves used the stress analysis of this Inglis. This Inglis is a talented professor. Graves is also a talented professor. So this talented professor used this talented professor's stress analysis and get this equation, and pi equals and pi 0 minus pi sigma square and A square B divided by E. E is a Young's modulus, sigma is remotely applied load, A is this fracture length, right? B is thickness, and pi 0 is a potential energy of uncracked plate. Uncracked. Suppose there is no crack, no this through thickness crack here. So this guy would have this pi 0 as the potential energy of this is uncracked body. For this cracked body, so we can pi for this one, and we can use this equation to denote the potential energy of this cracked body. Okay, I want you guys to know and this for this case scenario and how to calculate the potential energy of a cracked body. So this is very, very important. That's the reason I give this figure and this equation and at the very beginning of our today's lecture. Then I'm going to show you one example on how to use the Graves criterion and to solve this is the problem. But for this one, and we have this is sharp micro crack, right? This is a sharp micro crack at the tip of a microscopic crack. This is microscopic crack, and this is A1. So this is a 2A1. So this is remotely applied. This is applied load. This locally applied load here, but because of remotely applied load. This is the radius of curvature. Here is rho. Okay, and so we can see this is because the stress concentration. So this is a sigma local here, okay, and can be written as this 2 sigma, and this sigma is the sigma remote infinity, and square root and A1 divided by rho. So this assumption is that this A1 is much larger than this rho, right? So let's read this is a statement. A flat plate made from a brittle material, okay, brittle material, and contains a microscopic through thickness crack, and with half length A1, this half length A1, and notch tip radius rho, not tip radius rho, okay, a sharp penny-shaped micro crack, right? Penny-shaped micro crack with radius A2. This radius is A2. This so radius is A2. So this one will be the diameter. That's the reason this guy is called 2A1. It's located near the tip of the large floor. This larger floor, and so this guy is near the tape. This is the tape of this larger floor, as illustrated in this figure on 2.5. Estimate. Our task is to estimate the minimum size of the micro crack required to cause failure in the plate, and with when this Graves equation is satisfied and by the global stress and A1. So we want to know, so this is a minimum size of a micro crack required to cause a failure in the plate. So we want that is a critical condition, right? So we have learned how to calculate the stress concentration factor, right? If we have nominally remotely applied load and for given crack, and how to calculate the stress concentration factor. And we also know that, and given this is a through thickness crack, and how to calculate, in this case, sigma F, the failure stress. And we also know, and given a penny-shaped crack, and how to calculate this case is a failure, the stress. We know these 3 equations. And today we are going to use these 3 equations and put them together and to solve this problem. Let's see on how to solve the problem, okay? And our goal is to find the critical A2 at which, so this is, if we have this applied load and it will crack, it will crack. So we know that the condition is that sigma infinity, okay, sigma infinity equals sigma failure. So that is the condition. So we also know that sigma local, right, and equals sigma infinity multiplied by 2 and square root A1 divided by rho, and because of stress concentration. So and suppose, look out here, suppose we have this remotely applied load, a lot far away from this crack tip. Well, this is a local stress, and this local stress can be written in terms of this equation, and because of the stress concentration, right? So this is sigma local. And so this for this Griff's criteria for through thickness crack, and we know that sigma F equals 2E multiplied by gamma S. Gamma S is this is gamma S. Gamma S is a fracture energy per square per unit square. So this is gamma S and divided by pi A1. And so this is sigma F equals this, right? 2E gamma S pi A1. And for this is a penny-shaped micro crack, and we know that sigma F penny equals 2 pi E gamma S 2 square root 1 minus nu square multiplied by A1. Okay, so this is sigma F is and the load, the failure load that you apply on this is a penny-shaped micro crack. So this one, because we know that, so this is because of stress concentration. So this local stress applied on this local stress applied on this is a penny-shaped crack will be 2 sigma square root A1 over rho. So this equation and can be established. This is the failure stress and based on the penny-shaped crack. So this is stress is this is a failure stress. Okay, this is failure stress, and then multiplied by this is the stress concentration factor. So then this after we get this equation, and we have one equation. This is one unknown, which is A2, and we can get write A2 in terms of this is in terms of pi square rho, and this is Poisson's ratio, and for a given Poisson's ratio which equals 0.3, and we can calculate the A2. Right? So this is and how we solve this problem. Any questions so far? So you can see, and we used 3 equations we have learned in our lecture 3. Okay? Any questions so far? Okay, great. Okay. And then next section, and we are going to talk about energy release rate. So energy release rate was proposed by a talented Professor Irwin in 1956. So this energy release rate and can be defined as this is a G. Okay, this is G equals negative, and the derivative of pi. Pi is the potential energy of the cracked body. And with respect to the A is a cracked area. You should know that A is a cracked area. It is not a surface area. We know that cracked area is different from the surface area. Surface area is the double of this cracked area, right? So be very, very careful. So also this G energy release rate is also called the crack driving force, and either way will be okay, right? So we also know that, and given a cracked body and this energy release rate or this energy, this crack driving force can be written as a function of the geometry of the cracked body, the applied load, Young's modulus, and Poisson ratio. That is material property. For linear elasticity, and we have Young's modulus and Poisson ratio. Okay, so we just focus on Young's modulus and Poisson ratio because now we are focusing on linear elastic material. So this is because I just at the very beginning of this lecture I showed you for cracked body that with through thickness crack and how to calculate and this case a potential energy. We have this equation, okay? So this is pi equals pi 0 minus pi sigma square a square b divided by E. E is Young's modulus, and pi 0 is the potential energy of uncracked body. Okay, uncracked body. There is no crack. If there is no crack, and this guy's potential energy is denoted as pi 0. Because there is a crack, and so this potential energy, excuse me, is written in terms of pi, and this pi 0 needs to be deducted by this value, and which is closely associated with the size of this crack, right? And we also know that dA, right? dA equals, because A equals 2A multiplied by B. 2A is a crack area. 2A is a crack area, right? So this is a surface. The this is a through thickness crack, right? So this surface equals, and A equals 2A, the length multiplied by the thickness, that is a crack length. So this one can be written as 2B and dA. So A is changing because we are thinking about this energy release rate, which is associated with the crack length. So A is changed, B remains constant. So because pi is constant, okay, if we just plug in this substitute the pi into this equation, we will have this. G equals pi sigma square A and B. This will be gone because this guy is a constant. And so this is based on this term, and we have, because dA can be written as 2B multiplied dA, and so we can simplify G as pi square sigma square A divided by E. And so this is energy release rate, and which is closely related to the geometry of the cracked body, the crack length, right, including the crack length, applied load, Young's modulus, and Poisson ratio, right? So if G equals GC, and GC is a critical energy release rate, and which is, our assumption is that GC is a material property that does not change if this the crack length changes, or this is geometry of the cracked body changes. This is constant independent of crack length and also the geometry of the cracked body. This is our assumption, okay? And we also know GC can be written as dWs divided by dA, and dW, this is derivative, I'm saying, derivative of Ws with respect to A, and Ws is work to create a new surface, and Wf is a fracture energy. Okay, this is fracture energy, we talked about it in our previous lecture. And this includes the plastic, viscoelastic, or a viscoplastic effects depending on material. And you should know that, right? Any questions so far? Okay, if there's no question, let's move on to the next one. So the potential energy of an elastic body, and we know potential energy, here is a potential energy, right? This is potential energy. Potential energy of an elastic body can be written as using this function, this equation. Potential energy equals U minus F. And U is denoting the string energy, and stored in the body, street energy and stored in the body. F is work done by this is external forces. This work is done by the external forces. And this is a strain energy minus this work done by the external forces, and we will get the potential energy of elastic body, right? So this is, you should know that. And then I'm going to introduce these two different loading styles. One is a load controlled loading, and another one is a displacement controlled loading. I want you guys to know these two loading approaches, okay, or styles, and why it is very, very important. I will, even though I do not require you guys to do some experiments and to do some experiments for this course, but still want to prepare you guys, and this is necessary skills and knowledge about and how to conduct experiments related to the fracture mechanics, the specimens. Load controlled, as the name suggests, the load is fixed, right? And load is fixed. Load fixed means that the load, I will not change the load. And for different case scenarios, I keep using the same load, right? So look at this one. So look at this figure 2.7. So here, suppose this is just a schematic. This is a representation of this is a load controlled loading. This is an approach. So here is a cracked body, edge crack. The edge crack equals A. So here is a weight P, right? And so this is connected at this end, and we can see that, okay. So F, the load, the work done by the external force, the P is the external force. F equals P multiplied by delta, right? So this delta, I suppose I go here, I have this delta, and P, right? P, the load multiplied by delta equals the work, and then I calculate this is a straight energy, and the straight energy equals what? And straight energy for this straight energy, and can be integrated, or can be get by integrating this P multiplied by d delta, right? D delta, P multiplied d delta, and from 0 and to this is delta. Do you understand, guys? Okay, so this equals P dA, and from 0 and to delta, and for graphically, for this one, we can see that, okay, I have this is A, this is for my crack length of A. So this is for my crack length of A plus dA. dA is very small. And we should know that if the load does not change, a longer cracker, this longer, if the crack is longer, and so it is more, it is more compliant, right? So you can get, for this load, for this one, I have get this is displacement, right? So this is displacement. And for A plus delta A, for this crack length, this is my curve. So this one is d delta. You understand, guys? D delta. So this straight line represents the crack length of A. And this straight line represents the crack length of A plus dA. So for the same load, if I use this crack length, the crack length equals A, and so this is my delta. And for A plus dA, I will have, this is my d delta. So you can see, so this U equals OBA. U equals, see, from 0 to delta, from 0 to delta P, right? Is P is changing. P delta A, we have O, B, A. So this is a triangle, and which equals 1/2 delta P, right? So this is a string energy. Then we get pi. Pi equals U minus F. This is my U, this is my F. F is equals P load because the P is a constant. And P delta, right? This will equals 1/2 P delta. 1/2 P delta, this is U equals 1/2 P delta. So this pi equals negative U. You understand, guys? Okay. So you should be clear that, so this curve represents the curve with the correct length of A. This straight line represents the curve of the correct length of A plus dA. So we just assume at another instant that for another case scenario, and the correct length equals A plus dA. So dA is very small. So then we can get this G is the derivative of minus of the derivative of pi with respect to A, right? So B, because B is constant, thickness is constant, and we could just take it out, and we have this pi equals minus U, this minus, so this minus sign cancels this minus sign. We'll have du dA and parenthesis P. The parenthesis P means that it's load controlled, right? So we also know that, so U equals 1/2 delta P, we just plug in, right? So this 1/2 is here, and P is constant, can be taken out. So we will finally will get D delta dA on parenthesis B. Any questions so far? Okay, so graphically, what does that mean, guys? And graphically, I'm going to show you, okay? So I labeled here as origin, and this point is B, and this point is E, and this point D, this point A, and this point is C. I labeled these 6 letters, 6 points using 6 letters here. So graphically, let me show you, okay? Graphically, du, right? And du equals OED, right? OED minus OAB. Do you guys agree? So U, the change of U from when the correct length equals A, and when it go to the correct length of A plus dA, so this one change. OED minus OBA, right? So these two guys, OED equals what? OED equals 1/2 base OE multiplied by the height, the final load value P, and the load value P, I'm sorry, the load value P here, minus OBA equals 1/2 the base OB multiplied by the P here, right? And so this gives us what, okay? So look at this one. This guy minus this guy. So this gives us 1/2 BE multiplied by P. So this is a triangle. OE multiplied by P. And this triangle, OB multiplied by P. This one minus this one. equals half BE multiplied by P. And then equals 1/2 AD multiplied by P equals ODA, and finally equals 1/2 P multiplied by and DA. Right? And then DF equals OEDC, the applied load, the load, OBAC equals this, equals BEAD or AD, the same thing, equals D delta multiplied by P. So this, the whole area, this area. All right? And then T equals DU minus DF, DA. And we have, this is P half, P delta A, DA, 1/2 P, DA, D delta DA, parenthesis P. And because DA equals B, D lowercase a, so we get this is our energy release rate for load controlled the case scenario. G equals P divided by 2B parenthesis D delta over D lowercase a parenthesis P. So we can mathematically explain this one, derive this one, and also graphically derive is how this G, how this G's equation. Any questions so far? Okay, guys. If there's no question, and we are going to talk about another, this is a loading condition. We call the displacement load, displacement controlled. So as the name suggests, the displacement is fixed, right? And displacement fixed for two case scenarios. One this is crack length equals A. Second case scenario is when the crack equals A plus DA. So as seen in figure 2.8. So you should know that delta is fixed and the testing machine is infinitely rigid. It's infinitely rigid. Okay, let's see how we derive this is energy release rate for the displacement controlled the loading condition. So D delta, okay, D delta equals 0 because the delta is fixed. For one case, when the crack length equals A, and to another case, when the crack length equals A plus DA, delta does not change. What does it mean? It means that from A, crack length A to crack length of C plus DA, so no external force, no work has done by the external force. Why? Because dF equals P, dA equals 0. This dA equals 0 because delta is fixed, right? No matter how your P changes. And the whole thing, dF equals 0. So as a result, and pi equals U minus F. F equals 0, F does not change. And so pi equals U. Pi equals U equals half P multiplied by U. Right? Then this G equals negative d pi dA, right? Because A equals, we know that A equals 2AB. So this one, this is 2AB, how we get here. So the pi, d pi equals, because d pi we just plug in, substitute to half PV here. Right? So you can have, this is the delta. Delta is a constant, so delta is taken out. We have dP and dA. Right, guys? Any questions? This half is this half. Any questions, guys? Because you should know that this is energy. This is edge crack. Edge crack A. The crack length equals the length A, not 2A. The crack is not denoted by 2A. Crack is denoted by 2A only for the central crack. For edge crack, the crack length is denoted by the crack length A. Okay, so this half is this from here. Any questions so far? Okay, let's look at our picture. Okay, so this one. So this one, and this is a crack length A, right? And if we change the crack length from A to A plus dA, so this is a D. This D does not change. This D does not change. That's a displacement control. And look at this picture. We have O, B, C, A. Right? Look at this one. So this one, and we can see clearly du, right? And du equals U is a straight energy. OCB, du equals OCB. OCB is for the new crack, A plus dA. Minus OAB, the older crack, OAB, right? So this one equals what? This guy, OCB minus OAB, we have this one is a shaded area and will be minus OAC. You should know that, because OCB in the area of OCB is smaller than the area of OAB. That's the reason we have negative sign here. Okay, it equals 1/2 delta, 1/2 delta is a triangle. Delta minus multiplied by minus dP. This is minus dP. Right? So this shaded area. This is the dP multiplied by from here to here. So that is the delta. So 1/2 because it's triangle. So this is negative. This is negative. We also here, and we also this is negative because, from A to A plus dA. So this is a load decreases if we want the same displacement. Right? So this equals 1/2 delta dP, and dP is changing, dP is decreasing, dP is negative. And then from here, and G equals d pi to dA, pi equals du minus df, df equals 0. So here, so this equals du is here. Okay, look at this, du is here. So 1/2 from here, negative is here, and delta dP, and the parenthesis delta. Delta means this is a displacement control. And so we can see delta 2B and dP dA, because dA equals A multiplied by d capital A equals B multiplied by and d lowercase d a, d lowercase a. So that's the reason we have here. So up to now we have for the load control system, and we have this equation. For decontrol system, and we have this equation. For compliance, if we introduce another concept, compliance is defined as the C, which equals the displacement and divided by rho. Actually, compliance is a reciprocal of this is the stiffness. Okay, stiffness is defined as the ratio of P and with respect to corresponding displacement delta. But compliance is C equals delta divided by P. So if you plug in, right? And this we can get G equals P squared 2B and DC dA. So this equation works for both L controlled and D controlled. And you can just plug in. And for this case, P equals, right? For this case, the delta is delta equals P multiplied by C. For this case, and P equals delta and divided by C. And you can just plug in and to see what you guys will get. Okay, so we get this equation. This equation is valid for both L-controlled loading condition and also D-controlled loading condition. Any questions so far? Okay, if there are no questions, and I would like to stop here and conclude our lecture today. And I hope to see you guys tomorrow, and so I can explain your questions if you have, answer your questions if you have. And I want you guys to go through this is lecture notes and before you go to the class. Okay, if this is the case, and you can have better understanding of this material.